thank you everyone for coming here. I would like to share you something about PaddlePaddle. PaddlePaddle is an open source deep learning platform originally developed in Baidu, the Chinese Google company. We have been running the system for 4 years, but as an internal system. Until September last year, we decided to open source it. By that time, many people have been asking me, why would you guys open source yet another one? Especially some people asking me, what's the difference between PaddlePaddle and Kubernetes? Here's the slide, trying to answer the question. The PaddlePaddle as TensorFlow, both of them have a business model. There are clear differences about business model, but this slide will be focused on how the business model will bring the two systems to different technical directions. So our journey started from a real requester for AI. Several months ago, the CTO of Changhong, one of the largest TV set manufacturers in the world, visited our Sunnyvale office. The CTO asked a question, can you help us to control our TV sets using voice? Like people can say, which channel is playing National Geographic, and the TV set should switch to that channel. So for most people who have been working in America, the first idea is about having an AI hub. How about Amazon Alexa? The people just talk to Alexa, and Alexa controls TV sets. But obviously, the CTO didn't agree with this option. Why should I base my product on another product of another company? Also, there's some problems with Alexa locating in a room, but people in another room. Actually, Changhong's high-end TV sets have been able to be controlled by voice for a while. What they did is to call a voice recognition API. The service has been provided by a Chinese speech company, but Changhong has been dissatisfied with the service because by the agreement, Changhong can't retrieve the user's voice data from the API provider. But anyway, Changhong would like to build their own service, speech recognition service for their own TV. Another option is to build their own AI on the cloud. But there is yet another problem. Up to now, we can't virtualize GPUs practically. So when we rent a GPU instance on the cloud, we actually rent a real computer, which means it's pretty expensive. Another reason is that most manufacturing business are not familiar with cloud as we do in the internet business. People are usually afraid of something they're not familiar with. So the only best solution would be to build AI on Changhong's on-premise clusters. And yes, that's what the CTO is looking for. Actually, in the East Asian market, especially in the China market, there has been a lot of smart devices, a smart appliance. For example, to the left corner is a voice-controlled air conditioner. This thing has been selling very well in the China market. An estimate said there will be 1 million more voice-controlled air conditioner than sold in the first 6 years of 2017. To the right is a voice-controlled TV. Such kind of a TV has been sold for 5 years. And many users have been using them. At the bottom is a third device. It's a mirror in the car. It's not a just a mirror. It's an Android device, actually. We can talk to the device, like navigate to somewhere, and you can see that some GUI will display on a mirror. So when we do AI, we like to find out what the customers we can serve, or how can we build our own value. So an easy survey would be something like, there are internet companies and non-internet companies. There are big companies and the small companies. It's a good idea to bring AI to the cloud. I think that's what TensorFlow people has been working hard too. When we use TensorFlow, it's pretty good. The document is good. The community is great. We can easily program something on our laptop. But if we are going to run huge models using huge data, we might have to go Google Cloud. There, they runs the highly optimized distributed training configurations. But for these 4 cells in this graph, it seems that only small internet companies would like to use cloud. It's hard to imagine that big internet companies would like to use cloud. Right? It's hard to imagine we run Google search engine on Amazon AWS. The same thing happens in China. No way to run Baidu search engine on Alibaba Cloud. So it seems that cloud can cover only one of these 4 cells. Our focus is to the 2 cells to the right. That means traditional companies. Neither big one nor small one would like to use cloud. In order to cover those 2 cells, we might have to develop a solution which can be easily deployed to business customers. After working with our potential business partners, here comes the solution. You can see that to this figure, to the left of the figure, it shows some internet kinds like Brothers, mobile apps, and Internet of Things devices like the air conditioner and the TV sets and everything else. Such kind of clients talk to the speech API server hosted on a Kubernetes cluster. Here at the bottom of this figure shows Kubernetes. It is an open source distributed operating system. It's actually the open source version of Google Board. The distributed operating system has been running Google search engine and every other service for a decade. It's very important to have a distributed operating system because on top of that, we're going to run all kinds of jobs. The speech API server is just one of these jobs. The server would be able to log users' voice and any other interactions between the server and the client's mobile client's IoT. Such kind of data will be collected using standard services like AMD and Kafka. So we can write online data process jobs using Spark and offline data process jobs using Hadoop. The processed data will be fed into a speech model trainer written using frameworks like PaddlePaddle. The generated model will be continuously pushed to that server to improve the service quality. So a key point of this solution is that for most businesses, not for researchers, for businesses, it's very often that we want to run many kinds of jobs on top of a single cluster. By that way, we can build a highly efficient data pipeline. Actually, we can see a loop in this figure. This loop shows that we can actually build reinforcement learning using this setup. So this is a good idea, general purpose cluster. The key concept on the general purpose cluster is that we need a distributed operating system which can group a set of processes into jobs. Like in the previous figure, we have web service job, we have data processing pipelines, we have machine learning training jobs. Also, we want the service to be isolated and the system should support multiple users. We can imagine that the web service will log user behavior data, and the data will be fed to one or more machine learning jobs. One of these machine learning jobs might be the main machine learning job, which trains the model to serve the users. But at the same time, we can carry on several online experiments. We could have multiple machine learning models, machine learning jobs using the same data flow, and they train different models. And these models are used to serve small fractions of users, so we can try them online. We don't want to see something like experimental jobs fail and every job fail on this cluster. Instead, we want good isolation. We also hope that the cluster can support priority-based scheduling. For example, a high-priority job can preempt low-priority jobs, like a web service job might run more processes if there are many users joining. And at the same time, in order to free hardware resource for the web service, we might have to kill some processes in the machine learning job. There's a great advantage of having a general purpose cluster because a distributed operating system can try to schedule processes from different jobs onto the same node in this cluster. For example, processes of a Hadoop job might require network bandwidth, require disk I/O bandwidth, but processes of a deep learning job mostly demand GPU and CPU. By scheduling different jobs from different processes from different jobs on the same node, we can make full use of a node, make full use of the network I/O, disk I/O, GPU, and CPU. Actually, we notice that the general CPU utilization of a general purpose cluster could be up to about 70 or 80%. But for special purpose clusters like those managed using MPI, the CPU general utilization could be lower than 18%. That's 4 times better. It sounds great, but it also poses some challenges. It's true that we can choose to use the open source distributed operating system, but in order to make full use of the operating system, we might have to change paddle. Here comes the technical challenges to paddle. So as we talked before, at nighttime, during nights, there could be many users turn on their smart TV sets. There could be millions of TV sets talking to the web server hosted on our cluster. So at that time, we might have to kill some machine learning processes. That would make our machine learning jobs running slower, but we don't really want to kill the machine learning job. By freeing hardware resource, we can run more processes for the web service, so we can provide a high throughput service to the users. At the daytime, people go to work and nobody is watching TV, so we can kill processes of the web service in order to free enough hardware resource so we can run more processes in our machine learning jobs. This is called autoscaling. That makes full use of the cluster hardware. Autoscaling poses a challenge to the machine learning framework that we can assume that the number of processes in the machine learning training job is a constant value. Instead, obviously, it varies over time. To handle such kind of a challenge, we say we shall be able to handle fault recovery. The fault of processes might not only due to the bugs, mostly it's due to the dynamic scheduling. It's often that people talking about speed up when we publish paper about machine learning platform. As we can see, in an industrial configuration, speed up makes sense only if the system can implement full recovery. We want to speed up, but the constraint is that the system can do full recovery and to support auto-scaling. Here, let's see how the PaddlePaddle is going to support the thing. If we now run distributed deep learning jobs using TensorFlow or MLSnap or any other systems, we notice that we should have constant number of training processes, like here, trainer 1, trainer 2, and trainer 3. In addition, we can have one or more parameter server processes in the job. But for PaddlePaddle, we are working on a new configuration. We are introducing an additional process called the master. The master is the scheduler of this job. It enumerates all tasks and trying to dispatch these tasks to those leading trainer. Please be aware that it's the leading trainer. So it's reasonable that some trainers dies, get killed, get preempted by other higher priority jobs. Actually, it's okay for some of these parameter servers get preempted, but masters dispatch tasks only to those living trainers. And it's also okay for parameter servers to get preempted. Like in this figure, our design of parameter server differs from the Google's ones presented in the Distant Belief paper. In that paper, each trainer holds only part of the model, like each parameter server holds only part of the model. That design allows the system to train very, very large models. But however, we notice that in order to accelerate the computation in deep learning, we have to load the model into the memory of the GPU card. That means the model cannot be very big. It's true that we can train a very big model, but switching model between main memory and GPU memory means that we can't make full use of the GPU. It doesn't make much sense to have GPU. In practice, most deep learning models, from speech recognition to face recognition, all these models can fit into the GPU memory. That means every trainer can have its own complete local model. But we can notice that each parameter server here holds only part of the model. That's because of a special design of our parameter server to distribute network communication over multiple machines. We're going to have a blog post soon to describe more details here. But by this figure, we can see that because each parameter server holds only part of the model, so if any one of them dies, the only effect is that these trainer processes cannot exchange idea about that part of the model. It will be recovered once Kubernetes, the distributed operating system, restart the parameter server instance. By then, these trainer processes can go on exchange ideas about that model part. There is still a chance for the master process to get crashed or get preempted. In order to recover from a preempted master process, it's very important for us to place all those important data structure onto a reliable random access device, not just in the master's memory. We do so by placing the very important data structure onto etcd. etcd is a standard component of a Kubernetes cluster that provides an immortal key-value storage. In our design, we are going to maintain 3 queues on etcd. One of them is called to-do. At the beginning of a machine learning training job, the master process will enumerate all tasks, usually means some segments of the training data sets, listing all these segments and put all of them into the to-do queue. Then the master process can start dispatching these tasks to trainer processes. Once a task is dispatched, it's moved from to-do queue to the pending queue. And once the task is completed by a trainer process, the trainer process will report to the master process. The master process will further moving that task from pending queue to down queue. So at the beginning of the job, the to-do queue is full, the rest 2 queues are empty. And by the end of this job, the first 2 queues are empty and all tasks are moved to the done queue. It's also possible that some trainers get preempted and a pending task gets timeout because it will be never completed. By this time, the master process would move the pending task back to the to-do queue. To the right of this figure, we show that how the status of a task would change. A task will be created by the master and put into the to-do queue, and once it's dispatched, it's moved to the pending queue, or we can say its status changed from to-do to pending. If it's completed, it's moved from pending queue to done queue. Otherwise, if it times out, it's moved from pending queue to to-do queue. All the status are maintained on the etcd cluster, not in the main memory space of the master process. So even if the master gets preempted, once the Kubernetes, the operating system restart the master process, the reborn master process can get the data structure from etcd again. So here comes the general idea about the business challenge and how we're going to address the challenge by providing a technical solution. The community of Kubernetes has long been growing out of Baidu. I'm leading the Baidu Potato team to develop the system that our team had about 10 engineers, but you can see on GitHub, we're already having about 60 developers there. Given that we open sourced the system only several months ago, I'm pretty optimistic with the growth of the community. Let me get back to the short size depending on the GPU V-Vein. Awesome. Let me go over some questions. First of all, hey guys, can you hear me? All right. Some comments said there's weird frequency and echo. Okay, let me assume the sound is good. Auto-scaling is time controlled or triggered by other factors. Auto-scaling is mostly triggered by the user's behavior. Like I said, like we are running a search engine when there are many active users accessing the service, the distributed operating system would have to increase the number of processes in that service job. But by the same time, you might have to kill some processes in other jobs, usually those lower priority jobs. In the configuration I just shown in the figure, the machine learning training job usually have a slightly lower priority than the web service job, because even if the machine learning jobs get completely killed, the web server should still be able to run it to serve the users using the most recent model. The next question, do you optimize the shard size depending on the GPU VBANG? No, actually, we don't. Up to now, it's the developer's responsibility to make sure that model shards, actually, they just need to make sure that the complete model can be in the GPU VBANG. Because the training process does require that the model fit into the GPU VBANG. Yep, I know that's a challenge sometimes, especially when we do huge models like large vocabulary RNN language model. But still, I think we can do that because we can introduce more layers, so we have less parameters for each layer. Yeah, that's the idea. Deep learning, we can make the model deeper. Is there such a thing as bad data? It's how do you figure it out? I'm not sure if I understand the question clearly. If that's about something like collating noise in the data. If so, I can tell that for most industrial machine learning jobs, we do not clean the data at all. When we say the word noise, it actually implies the data distribution is the exponential family distribution, like Gaussian distribution or Laplacian distribution. But the real data sets in the internet industry will be always long tail. If we kill those noise and the data, we are actually cutting the long tail of that distribution. We will be assuming an unrealistic data distribution. So, in short, we do not claim data noise at all. For an example, when we do search engines ranking model using PaddlePaddle and Baidu, we won't delete those low frequency minor queries. We don't even try to filter out those typos, the words not frequently appear. Because we assume that if people type a typo, there will be a reason. It could be like the word is easily being wrongly typed. That's a pattern of our user. We type a typo to express an idea, so the typo is reasonable. We do not remove low frequency word. We do not remove typos. Instead, we accept that people might make typos. Yep. So the short answer is that we do not filter noise out at all. Okay, if no other questions, I would like to show you how everybody can run PaddlePaddle using Docker. I mean, without installing any other software on your computer. Let's go. As you can see, I'm having a terminal opened on my laptop. We can run a command, Docker run. This is a single command. We use Docker to run the Docker image because we already hosted the Docker image on that server called dockerhub.com. So please just type in that command. This command would download this Docker image to a local computer if you have not been doing so. It's running now. It tells that the Jupyter Notebook service has been running on this URL, so we can just click here. Good. Here it comes. With a notebook. We can type any chapter like fix or line. There is a Chinese version and an English version. Going to the English version. Here is a chapter of an open source book. It's called Deep Learning 101. It's mostly about deep learning, but there's example programs written using PaddlePaddle. Here you see that we are importing PaddlePaddle, and so we can handle the data under the training. So the next line will be initialize Paddle, and then we start to configure the model. We define a data layer whose name is X, and from the layer X, we do a fully connected layer to do the prediction. And given the prediction, we fit it into MLC cost layer. So that layer can compare the predicted Y and the real Y, that from a data layer called Y. Once we get the topology defined, we can derive parameters from the topology. Please be aware that it's very open that some layers of the topology will share parameters. So there's a separate step of deriving parameters from the topology. Then we create a trainer to train a model, and we pass a optimizing algorithm as a parameter to the trainer. Then we define a fitting. The data is loaded using a dataset package. So it's read into the memory as a stream, not totally loaded into the memory as we usually do when we do torch work or MXNet work or small data sets for TensorFlow. In PaddlePaddle, the data will be read always like a stream. So there will be no difference with online learning and batch learning. But we need to define a Python dictionary to specify the correspondence of columns to data layers. X and Y are actually names of data layers. After defining the fitting, we can also define an event handler. The event handler will be called by the train function to, we can draw plots. Let me show you how it works. Hit cell, hit run all, and it runs the train function. The train function calls event handler to plot the figure here. In this figure, we plot cost. But we can define any other event handler function to plot anything else you would like to plot. Here is an example. Actually, we can browse other examples like fit align is very silly, simple. The recognized digits will be slightly more complex. In this chapter, we shows how to recognize a nest of digits. That's still a simple application. This is written as a textbook. In this example, we can define different functions. Each function corresponds to different topologies. Some using very simple fully connected layer, some more complex one using convolutional layer. The program, the idea of the program is exactly the same as the previous one. And again, we can put cell, run all, and it trains the model. It's not plotting. Oh, it might be downloading the data. We're reading the data using a dataset MS to train. If we haven't packed the pre-downloaded data in the data image, I have to download the data. I'm not going to stop here. I would like to show you that once we get a model, we can load an image. and we can do prediction influence of that. Here we say not trusting. We trust. Okay, let's try this again. As you can see, we're currently in the release candidate version. When we run this Docker image, we typed 0.10.0 RC3. It's the third release candidate. Let's go find out what's wrong with this and update to the community later. That's all about the paddle at the right time. As you can see, we still have a lot of problems with it. Thank you very much for that we're working actively on solving these problems. And if there is any question or anything I can help, please feel free to use the one-to-one feature of this website, or just visit our GitHub repo. It's here. Just feel free to submit any issues, and feel free to book my one-to-one service. Thank you very much.